The Milky Way is our home galaxy and the galaxy we are most familiar with. From Earth, the Milky Way looks like a strip of stars, gas and dust painted across the night sky. If the Earth didn't get in the way, we would see this strip going all the way around us. This distribution suggests that the Milky Way has some kind of flat shape. Dark patches, called dust lanes, can block some of the background starlight. Trying to determine its shape is challenging. Because of its huge size, we cannot send a probe far enough out to take a selfie of the galaxy, nor would we be able to detect the signal from such probe if we could send one. Trying to figure out its shape is analogous to standing stationary in a forest and trying to map the forest from that one spot. Not only are we not able to move to different vantage points, there are also trees, bushes, rocks and hills that get in the way. We face similar kinds of challenges when mapping the Milky Way. Not only is the Milky Way vast, but many parts are obscured by dense dust and glowing gas, making observation more difficult. Modern mappings show the Milky Way is a barred spiral galaxy that is 100,000 light-years in diameter. The Sun is 28,000 light-years from the center. Its disk is 6,000 light-years thick where the Sun is located and gets thicker toward the center. On the disk are 2 to 4 spiral arms. It has a central bulge that is somewhat football-shaped. The galaxy halo is the spherical region around the galaxy where globular clusters orbit. The Milky Way contains around 300 to 400 billion population 1 and population 2 stars. Population 1 stars are younger populations found near star-forming regions. Because they are young, they contain many highly luminous blue stars. This gives these regions of the galaxy a bluish appearance. They are often members of open clusters and are generally high metallicity stars. Population 2 stars are older, redder, low metallicity stars found in regions where there is no ongoing star formation. Globular clusters are one example of population 2 stars. They are simply void of star-forming material. Stars in the central bulge are also population 2 stars. Their temperatures are generally too high for star formation. Population 1 stars, shown in yellow, orbit on the disk and generally all in the same direction. Our Sun oscillates back and forth through the disk with a period of about 10 million years. It gets pulled gravitationally toward the disk, overshoots, then gets pulled back again. It takes the Sun about 230 million years to orbit the galactic center. Population 2 stars, shown in both red and green, orbit with elliptical orbits that are randomly oriented, much like how Oort cloud comets in our solar system orbit the Sun. The Milky Way is composed mostly of stars. 85% of the mass of normal matter is in the form of stars and 15% is in the form of the gas and dust that makes up the interstellar medium. Most of that interstellar medium is hydrogen. Most of the hydrogen in our galaxy is atomic hydrogen, a proton, orbited by one electron. In fact, there is about 5 billion solar mass units of it. Knowing the distribution of hydrogen is not only important for learning the structure of the Milky Way, it's the main ingredient for making stars. It is important to map out where this atomic hydrogen is. One way to do this is to observe the locations of the 21 centimeter wavelength radio emission that comes from atomic hydrogen. To better understand the origin of this 21 centimeter emission, imagine a student has a bar magnet on a table and she holds another one above it so that their magnetic poles are aligned. Because like poles repel and opposite poles attract, the top magnet will flip around when she lets go of it, and they will clink together. The rotational energy comes from the magnetic potential energy the magnets previously had. That is, when released, They lose magnetic potential energy and momentarily gain rotational energy. In a hydrogen atom, electrons and protons behave a bit like little bar magnets. When the electron attaches itself to the proton, to form atomic hydrogen, its magnetic pole may be aligned with the protons, giving it a higher magnetic potential energy. The electron will spontaneously flip, going to a lower potential energy state while releasing a low-energy photon with a 21 cm wavelength. This process is called a spin flip. Not only is there atomic hydrogen, but hydrogen can also be ionized or in molecular form. What form it's in gives us clues to what's happening in the regions of the Milky Way where it is found. Nebulae are large clouds of hydrogen, made visible by interactions with starlight, by nearby stellar explosions, or by the 21 cm radio emission. Because nebulae are large and bright, they can be seen from large distances. Emission nebulae are high-temperature regions where much of the hydrogen is ionized. Because of the high temperatures, the hydrogen tends to be diffuse, or low density. When electrons are recaptured to form hydrogen atoms, photons are emitted as the electron drops down to the ground state. Emission nebulae are emitting their own light, which usually has a pinkish appearance. Shown is an emission spectrum from an emission nebula. Each upward spike is an emission line. Emission nebula are associated with supernova. Atomic hydrogen not only emits the 21 cm radiation, but it can also scatter nearby starlight. This gives them a bluish appearance, for reasons similar to why our sky appears blue. These nebulae are called reflection nebulae. They are 100 to 10,000 times cooler than emission nebulae, but still far too hot to form stars. Absorption nebulae are dense cold clouds of molecular hydrogen and other material that block background starlight. These clouds are a few tens of Kelvin and are where stars began to form. One can think of stars as being the factories that make heavy elements out of hydrogen. One can also think of galaxies, like the Milky Way, as factories that make stars. There is a circle of life for stars. Stars form from cold clouds, spend their lives making heavier elements in their cores, then die, tossing material back out into the interstellar medium that is more enriched with heavier elements. New generations of stars then form from this enriched material. The more generations of stars there are in a region, the more metallicity that region has. Stars emit very strongly in the visible part of the spectrum and can thus be easily observed using optical telescopes. Large stars die explosively, heating up their environments and giving off gamma rays and X-rays. Emission nebulae are associated with these events. As the gas cools, ionized hydrogen becomes atomic hydrogen, which is associated with reflection nebulae and 21 cm radiation. As the gas gets downright cold, it is often seen as absorption nebulae or detected by low-energy radio emission. When stars began to form in these clouds, they emit infrared radiation. Atomic hydrogen will reveal itself by the 21 cm emission. Observing the Milky Way using multiple wavelength domains gives us a clear picture of how it is structured and where star formation occurs. Shown on these images are 360-degree views of the entire Milky Way at different wavelength domains. Locations where we observe radio emission from carbon monoxide are locations where there are cold star-forming clouds. Regions where we observe infrared emission are regions where stars are forming. Places where we observe gamma rays and X-rays, stars have recently exploded. Places where we observe reflection nebulae or 21 cm radio emission is atomic hydrogen. It appears that most of the star formation occurs on the spiral arms. Shown is an image of the Whirlpool Galaxy, a galaxy similar to the Milky Way. Note the dark absorption nebulae on the arms. Since large stars don't live very long, they go supernova before they get very far from where they were formed. Thus, we also see the pinkish emission nebulae on those arms, right next to absorption nebulae.